Hello, I'm Schwa, and if you let me, I'd love to be your math teacher. Today, we're going to be talking about the natural numbers, and this time the camera is going to be more stable than last time, so tell me in the comments whether you think that's better or not. I don't know, I'm kind of figuring this out as I go. So we're going to be defining the natural numbers. I mean, we kind of already did last time, right? We laid a lot of the groundwork. We had the von Neumann numerals, which we can use to, technically speaking, define the natural numbers in terms of sets, right? But technically, we don't really need to know about that. That's sort of more of a technical detail because, of course, in practice, natural numbers are just the numbers 0, 1, 2, 3, 4, and so on. The familiar counting numbers, like how many apples are there on the table. And 0 is not always included in the natural numbers, but I like to include 0 for reasons that I explained in the previous episode. All right, then we're going to look at addition of the natural numbers. And addition is going to satisfy some familiar properties like commutativity and associativity. We're going to get to those. And there's a lot I could say about associativity, but maybe I won't go into so much detail in this video. And then we're also going to look at these what's called order relations. So this is a very fancy term, but basically order relations. And basically the idea is it's to sort of describe which numbers are bigger than other numbers. And of course, that can generalize to different kinds of objects too, not just numbers. So maybe sets or maybe something else. So which is bigger, right? That's what order relations try to describe. And we're going to get into relations too in more detail in an upcoming episode, I think. But it's important to get some sort of high-level overview of what's about to come, right? So for example, 3 is less than 5. That is an order relation, and there's different kinds of order relations. There's partial orders. There's total orders. And then there's, you can have a well ordering. So we're going to finally look at the well ordering of the natural numbers. And this is how we commonly denote all the natural numbers, the set of natural numbers. It's with this n with an additional line here. And then finally, or I guess maybe somewhere in between, we're also going to show that there is an infinite amount of natural numbers. So that's pretty exciting. What's infinity, right? This is going to be our first introduction to infinity. And certainly, if there's any math majors watching in the audience, you all know there's a lot to be said about infinities. So maybe we'll get to that in more detail a little bit later as well. There's a lot of stuff here, but basically we're just gonna kind of go through this stuff one by one, and some of it's maybe going to be familiar, some of it is going to be less familiar, and we'll just see how it goes. Right. So So first of all, yes, the natural numbers are 0, 1, 2, 3. They can be used to count things. And presumably, a lot of you all know how natural numbers can be added together, right? So let me just give you some examples over here. So for example, if we have 2 plus 3, then, I mean, there's probably plenty of ways you can compute that. You can raise 3 fingers. Let me try to do that, and 2 fingers, and then count the total amount of fingers. And it's like, yeah, it's very difficult to move my fingers with my headset right now. But, there's 1 and 2 on this hand and 3 fingers on this hand. So in total, there's 5. 1, 2, 3, 4, 5, right? So, we could also draw the real number line, right? So there's 1, 2, 3, 4, 5. We start at 2, and then we move 3 to the right. So 2, 3, 4, 5, right? That puts us at 5, right? The result of this is 5, right? You all know how that stuff works. But there are some properties that this operation satisfies. And, maybe, those of you without, math training in the audience, you probably wouldn't even think to ask this. But honestly, it's like a good thing to wonder, like, what this thing even is. Like, what is an operation, like, in general? And it turns out that these orders, partial orders, these can actually, these orders, they turn out to be relations, right? So there's this sort of like side quest, right? So that there's this side quest where we have relations, and then those can be used to define functions. I hope you can all see this, probably. Functions, and then functions are actually, or operations then are specific kinds of functions, right? So functions can be used to define what an operation is, right? And this plus right here, it's a binary operation. So binary means that there's 2 things, and it means that there's 2 arguments that the operation takes in. So it takes in 2 and 3, so that makes this a binary operation. On the other hand, we could also have unary operations. So for example, if you put a minus sign in front of a number like this, so we have -5, then you could interpret this minus as an operation that takes in a single number, as opposed to this plus taking in 2 numbers. So this is a binary operation, while this is a unary operation. Yeah, I'm definitely getting carried away here. But this idea of how many inputs an operation takes in, that's called the arity of the operation, right? So there's a lot to be said about operations in general, right? Like, even though we all know what addition is, it's interesting, like, if you think about, like, what it really is, or what other things it could be, or, what are operations in general, then there's a lot to be said here. So this could be a unary operation, while this is a binary operation. I'm not going to write down binary because I don't know where to write it. I'm running out of space here. So there's this side quest. And honestly, this side quest, we're going to get to it. Don't worry, we're going to get to it. But right now, I will kind of just sidestep all of this. Actually, probably going to sidestep all of this for a while. I think first, I want to build up an understanding of these operations that we have, addition, multiplication, etc., and then also the different types of numbers, right? So today we're dealing with the natural numbers, right? But as you all know, there's also the integers, right? And there's the rational numbers, and there's the real numbers, and there's more different types of numbers after that. So I want to first try to build up all the numbers and their operations that we can play around with. And then after that, maybe we have a little bit of mathematical confidence. And most importantly, we have mathematical objects that we can play with. So then we can take on this quest of figuring out, well, what are relations, what are functions, what are operations, and how does that, how can we use those to better understand these familiar concepts like addition and multiplication, right? But all in due time, right? I think it's important to not get too carried away with the abstract math craziness, because this is pretty abstract, and you're not necessarily going to be able to appreciate this in all of its glory until you know about different types of numbers, even though, strictly speaking, it is a little weird to be defining addition and multiplication without first knowing what a function is, because technically this could be thought of, and it is essentially a function, right? So technically I'm doing things a little bit backwards by not beginning with this side quest and then defining addition, perhaps very formally. But I think it's more instructive to just take a look at these objects that we have and these operations that we can define on them, and trust that we know what operations kind of are intuitively, and then later we can get more to the nitty-gritty, hopefully. So that's the plan. So for right now, let's forget about this. This is just a dream that we will get to maybe eventually, but not right now. Okay. Let me try to not get too carried away here. So one property that this addition operation has is commutativity, right? And that's pretty obvious, perhaps, because we're used to the idea that if there's 3 balls over here, and then there's 2 balls. Oops, what am I doing? Oh, my VRChat camera is blocking my view. So there's 3 balls here and 2 balls here. Now, it doesn't matter whether you count the 3 balls first and then the 2 balls, or if you count the 2 balls first and then the 3 balls. So these are the same thing. And the name of this property is commutativity. Commutativity. And we say that addition commutes, right? That's what we say. So commutativity and something commuting means that we can swap these around and it's the same thing. So commutativity, conceptually is actually very, very easy to understand. And if you want some intuition for what types of operations you might expect to be commutative, then consider that if your operation is sort of symmetric with respect to your argument, then perhaps it's going to be commutative. So if your arguments kind of perform the same role, you don't really differentiate between them, then presumably your operation is going to be commutative. So for example, if we consider 2 points in space, right? So let's say there's this point in space and this point in space, on the number line. Now, if we define the distance between this point and this point, let's say there's some operation, some distance operation, right? Where we plug in this and then say dist and then plug in this point, right? I should maybe write this down somehow. Yeah, and I don't want to use too scary looking math notation here. But let's say, well, maybe I won't get too philosophical here, but you can think about an operation that would take in 2 points and then tell you the distance between those 2 points, right? So instead of having 2 and 3, you would have 2 different points in space, right? And of course, I don't know how you would represent those points. I don't know. Let's not get into that right now. But you would have 2 points and output that distance. And then it's pretty obvious that the order in which you give the operation the 2 points does not matter because you're just looking at the distance. You don't care about like which point you give first, basically. So the sort of distance operation between 2 points, you would expect that to be commutative as well. So for example, distance is a commutative operation. All right, wonderful. Now another really important property that addition satisfies is associativity, right? Now how do I think about associativity? A great example of an associative operation, in my opinion, is string concatenation. If you're a programmer, you're familiar with what that means. If you're not a programmer, then let's think of PlayDough. And hopefully this is going to make sense. So we're going to have, should I maybe get different colors? That would move the camera though, so I don't know if that's worth it. Yeah, maybe I won't get different colors. Let's just hope that this works. But basically, let's say we have an operation that connects 2 different blocks of PlayDough. So maybe having a square of PlayDough, maybe that's not so realistic. Let's have some clump of PlayDough, and then let's have some other clump of PlayDough. And then we're gonna, let's say the plus operation connects these 2 clumps of PlayDough, right? So the result of this operation would be a clump that's basically this clump and this clump like attached to one another, like together, right? Okay, maybe this is just looking like a mess, but hopefully you get what I mean. So we take this, then this clump of PlayDough, and we squash them together, and then we get this, right? So this is this combining PlayDough operation, right? Now this operation is associative. Now let me try to maybe draw PlayDough that is not just a mess. So maybe we have a heart-shaped piece of PlayDough in the middle, and then there's a square. Let me see, square here. And let's combine this. And parentheses, as you will see, they're a way to group an object together, and you can influence the order of operations and stuff like that. You know, maybe you have PTSD from middle school, where you had PEMDAS or BODMAS or some mnemonic for remembering the order of operations. Yeah, we're not going to be having much of that here. But anyway, that's probably a discussion for another time, or maybe a discussion I will never have, because frankly, I'm so sick and tired of seeing those videos on YouTube where it's like they have like 2 plus 2 and then this division symbol and 3 plus 1, and then they're like, what does this equal, or something like that. And you know, I don't even remember the exact ones, but anyways, let's maybe forget about that. That's an angry rant for another time. Yes. But here, back to our PlayDough example. So what's a third shape? Well, let's have a triangle shape here. So the result the result of this operation, what's that going to be? Well, that's going to be this triangle attached to this heart first, right? And then after that, we attach the square, right? So let me, I guess we'll just do this step by step. So first, when we attach the triangle to this heart from the right, then we get this expression. So we get a heart and a triangle attached to one another. And then when we finally attach the square, we get the whole figure, right? Now, as you might guess, doing this, so here what we did is we had a heart in the middle, and then we added a triangle from the right, and then a square from the left, and we got this, right? And these are parentheses here. Yeah, I don't know why I put parentheses here. You know, it's my math brain being stupid. Yes, so we could alternatively, right? We could add the square from the left first, right? Add the square from the left first, and then add the triangle. And now in this case, right, adding the square from the left, we get this, and then we add the triangle, and then at the end, and hopefully this is going to show on camera, I think it's going to be fine. At the end, we're going to get the exact same thing, right? So, yeah, this is the same thing as this. So adding this triangle from the right and then this square, right? It's the same thing as adding the square from the left first and then this triangle, right? So this combining PlayDough operation is associative, right? So an associative operation, the way I would advise you to think about it is that there's some middle element and then the order in which you sort of modify it from the sides, that doesn't matter. So, you know, we also could have had a string concatenation example if you're a programmer, but I don't know if everyone's a programmer, so I decided to go with PlayDough instead. But yes, that's associativity. Now, a very freaky thing about associativity, actually, and now I might be running out of space. I don't know. But a freaky thing about associativity is that, hopefully this is going to show, I think it's going to show, is that if you have a very long expression, so let's say I had 1 plus 2 plus 3 plus 4 plus 5, then, okay, I actually haven't said, or maybe I have said, that addition is associative. But anyway, addition is associative. And the reason for that, of course, is that if we have this 2 here, you know, it doesn't matter whether you add 1 to it first and then 3, or if you add 3 to it first and then 1. Because at the end of the day, you always add both 3 and 1, and the order that you do that in, it doesn't really matter so much. So that's why addition is associative. Now, it's not necessarily obvious, but a consequence of associativity is that we can evaluate these operations in any order that we choose. So for example, we can first evaluate this to be 7, and then maybe this to be 3, like that, and then plus 5. And now we can maybe evaluate this to be 13, and maybe add 3, you know, and this to get 16, right? So we can evaluate these in any order that we choose, and to me that's highly not obvious. I'm not from the you know, definition of associativity, but I'm not gonna get into that right now in much detail. Maybe if you all are interested, I could do a follow-up video at some point. But it's helpful to know that if you have a long, you know, lots of these different operations, then if your operation is associative, then we can do these do these in any order that we wish. And that's why this sort of expression doesn't need parentheses, right? So maybe by default, you would put 1 plus 2, and to that you add 3, and to that you add 4, and to that you add 5, and you would have like all these different parentheses, right? But you don't need to do that if your operation is associative, because it doesn't matter which order you compute stuff in. Okay, so we have covered associativity, commutativity. I guess now we can finally start getting to the fancy, spicy stuff. So order relations. Yes, for this, I think we're gonna require a little bit more space. So I will move. I guess I'll take my eraser with me probably. Okay, let's move. Ooh, and now we should get more space over here. Yay. Okay. So maybe I should, here we go. Perfect. So what were we going to talk about? Order relations, partial orders. Yeah, well, okay, so the basic idea is pretty simple, right? So we have the set of natural numbers, right? And, as we learned in the previous episode, we can define a set by opening curly braces and then listing out the element, right? So we can essentially define or describe the set of natural numbers like this, or denote it like this, and that's wonderful. So we have the set of natural numbers, which is a set that contains 0, 1, 2, 3, and so on. Great. So we're familiar with the idea that, for example, 2 is less than 3, right? That's, in fact, it's also less than or equal to 3. Isn't that crazy? That's all fine and dandy. But, these order relations, they're very, general things. So you can have a partial order, or you can have a partial order, or if your order is very, very nicely behaving, then you can have a total order. Now, the natural numbers actually have a total order. So this right here is a total order. So, but some orders are only partial orders. Now, every total order is also a partial order. So we could say that the size of natural numbers, that's both a partial order and a total order. But in general, a partial order is not necessarily a total order. Okay, but what's the difference, right? What's the difference? Well, a partial order, it's like you have skyscrapers, and you have many different skyscrapers. So I forgot, there was a term for it. Is it the skyline of a city? It might be the skyline. So imagine this is the skyline of a city, and you have different skyscrapers, right? That's a partial order, effectively. But a total order, well, what is that? Well, that is basically one really big skyscraper. Okay? Right? So a total order is just one big skyscraper, while a partial order is many different skyscrapers. Now, natural numbers, right? They have a total order. So they have one big skyscraper. Now, what is the skyscraper? Well, let me show you. 0 is less than or equal to 1, which is less than or equal to 2, which is less than or equal to 3, which is less than or equal to 4, which is less than or equal to 5, which is less than or equal to, and so on, right? So that's like one big skyscraper. I guess in this case, it's more like a train because I laid it out horizontally. Maybe I should have laid it out vertically instead. I don't know. But it's like this one long continuous, not continuous. Let's not use that term. Contiguous array. Is that too programming related? Okay, I don't know. This huge, let's call it a train, for lack of a better word. It's one number after the other, and there's like no other train like this, in the sense that every element is a part of this train. So it's one big train that, defines all the elements. That's very nice. All the elements are included in the train. But with a partial order, for example, you might have several trains, right? So several skyscrapers. So let's take an example, right? So if we have sets, right? Let's have subsets of the natural numbers, right? So last time I told you what a subset was. So a subset is a set where every element of that set belongs to the bigger set, right? So for example, right? So the set 0, 2, 4 is a subset. This is a subset of the natural numbers because every element from here is a natural number. It belongs to the set of natural numbers, right? Now, what would be an example of a set that is not a subset of the natural numbers? Well, -1, -3, and 4. That's not the right bracket or curly brace, whatever. I have the eraser here. Okay, there we go. All right. So this is not a subset of the natural numbers because, for example, -1 is not an element of the natural numbers, and neither is -3, actually. But we only need one outlier, and then it's not a subset. One outlier is enough, right? So this is not a subset of the natural numbers. But this is, because 0 and 2 and 4 are all natural numbers. Right. Now, we could, right, I mean, now at this point, I'm just kind of starting to play around with all this notation, terminology, but basically, we could define a set with all the subsets of the natural numbers, right? So we could have, the way that's usually denoted is you have some sort of calligraphic P, I think. Okay, I'm probably drawing this horribly, but you have some sort of P of the natural numbers, and it's basically every subset of the natural numbers, right? So, every subset of size 0, that's just the empty set. Every subset of size 1, well, that's already going to be an infinite amount of different sets. And then you can have a subset of size 2, so that would be 0 and 1, for example. I mean, there's a lot of sets. There's a lot of sets included in the power set of the power set of the natural numbers contains a lot of elements because it contains every single subset of the natural numbers. So if your set, if every element in your set is a natural number, right, then in that case, you belong to the power set of the natural numbers, right? So let's say I'm a set, and I contain 0, 2, and 4. Well, that means I belong to the power set of the natural numbers. I belong here to this set because all my elements belong to the natural numbers. Maybe this is confusing. I don't know. Maybe it's a little scary the first time you see it, but that's okay. We're just playing around. It's not like there's going to be an exam at the end of this video, so don't worry. So the power set. So back to these order relations, could we define some sort of like something that would describe the size of these subsets? Well, we could order them with respect to inclusion, right? So for example, right, the set containing 2 and 3 it's in some sense smaller than the set containing 2, 3, and 4, right? Why is that? Well, because it is a subset of 2, 3, and 4. Let's remember the Venn diagrams. So if we have a Venn diagram here, then 2 and 3 are all contained within 2, 3, and 4. And listen, I said that sets can contain duplicates in the last video, and here I have duplicates. So, yeah, sorry about that. I guess, you can, if you know what you're doing, you can break the rules with your diagrams. Because again, this isn't a math exam that I'm going to grade, so just do whatever you want. But anyways, so this 2, 3 set, or the set that contains the numbers 2 and 3, it's a subset of the set that contains 2, 3, and 4, because yes, and the set that contains 2, 3, and 4, that is a subset of all of the natural numbers, right? So this is all the natural numbers are here, right? So there's this set hierarchy. Cool, and it turns out that this it's called set inclusion, this operation, or relation, even though it's like the subset symbol, right? Basically this defines a partial order, right? Now, when I talked about partial orders, I said that there can be different skyscrapers, right? So what on earth do I mean by that? So for example, here, if we define this set inclusion as the partial order on the power set of the natural numbers, so all the subsets of the natural numbers, then in that case, one of the towers that we could have, right? I feel like I'm running out of space. Oops. I'm trying to get up here. Okay, so one of the sets that one of the chains that we could have is this chain of even numbers. So a set containing 0 is contained within a set containing 0 and 2, which is contained in a set containing 0, 2, and 4, and so on, right? So this is one train, right? But then we could also have another train, right? So we could have a similar train, but with odd numbers. So a set containing 1 is contained within a set containing 1 and 3, which is contained in a set containing 1, 3, and 5, right? And now, here's the thing. Like, in the case of natural numbers, if you have a natural number, then it lies somewhere within this chain, because you can compare it to any other natural number, right? But here, if we take, for example, this set containing 1, 3, and 5, it doesn't belong anywhere inside this chain containing these even numbers, because, it doesn't make any sense, because, hold on, I gotta think about this. Hold on, I gotta think about this for a second. Certainly, yeah, right. Because if this idea with this inclusion is to compare two sets, right, and say that the set that is contained in the other set, that's the smaller set. So for example, 0 is contained in 0 and 2, so this is the smaller set, this is the bigger set, and this is even bigger, and this is even bigger, and so on. But here, if we take the set containing 1, 3, and 5, then you can't really reasonably compare it with this set containing 0 and 2 because neither one is contained within the other. So which is the bigger one? Which is the smaller one? I mean, of course, you could say that, well, this one contains 2 elements, this one contains 3 elements, so this one is smaller. But that was not our order relation. We're ordering stuff with respect to inclusion. We don't care about how many elements the set has, right? So, you know, from the point of view of which set goes inside the other, you know, we can't compare these two. So we get these different chains. Whereas with the natural numbers, you know, you can compare, for example, 67, you can compare it with each of these numbers, so you can find where that number must reside within the chain, right? But that's not true with the subsets of the natural numbers ordered with respect to inclusion, because you can't compare all the subsets to each other, so you can't possibly say where this 1 and 3 should be in this chain, for example, because, you know, you can't compare it with any of these. So what do you do? So this partial order, we have different skyscrapers, different trains, right? So this is a partial order, right? Let me draw some kind of arrow here. So these different trains, this inclusion, or this ordering with respect to inclusion is a partial order, while the natural numbers exhibit a total order. So there's a very nice order that we have for the natural numbers. That's very good. And I haven't even defined what the order is, like, formally. I mean, I haven't really defined anything formally in this video, but I mean, that's kind of not what I want to do, not the point here. I mean, you all know what it means for 3 to be less than 4, so maybe that's all good. You know, just trying to give you the right ideas, right? If you get interested about this stuff, then you can look all these things up on Wikipedia and try to understand it better if you want to. Anyway, where was I? Right, there was a third thing, right? So there's actually so we can have a partial order, and we can step it up into a total order if there's only one skyscraper. So, you know, a one skyscraper, that's also a partial order. So it's but a total order is not necessarily, or a partial order is not necessarily a total order, but a total order is always a partial order. But there's a third type of order. I could actually, like, draw a Venn diagram of the orders. But first, let me get some more space here. I think we're gonna benefit from a little more space. So, basically, we have, like, partial orders. That's like, you know, it's relatively simple to define a partial order. So there's a lot of partial orders that you can define. For example, set inclusion. Set inclusion, that usually forms a partial order. And then within partial orders, we can have total orders. And all total orders are partial orders, but not the other way around. So, for example, set inclusion is not a total order necessarily, but the ordering of the natural numbers, you know, which number is bigger, that's a total order. But then within total orders, there's also there's an even more specific type of order called a well ordering. Well ordering. Now, what does well ordering mean? Right. I actually have to apologize in advance because I don't have an example of a total order that would not be a well order, like, that I could come up with right now. So maybe I'll give one in the description or something. I don't know. Sorry about that. But basically, what is a well order? A well order is a total order where every every subset, so any set of your elements has a least element with respect to your order, right? So in the case of natural numbers, right? Okay, I will admit I don't remember the formal details. I don't know if it has to be like a unique least element, but well, in this case of natural numbers, it is going to be unique because a total order just forms one row, right? Okay, you probably don't know what I'm talking about, but anyway, I'm just thinking out loud, basically. So in a well ordering, and we say that if there's a well ordering, we say that the set, so the set of natural numbers is well ordered, right? That's what we say, is well ordered, because there exists a well ordering of the natural numbers. Well ordered. Great. Okay, now what does this mean? Well, let's consider some examples of subsets of the natural numbers. So we could have 2, 3, and 5, for example. So here, what's the least element? Well, 2 is a least element. So this set has a smallest element, and in general, it doesn't matter what set you consider. It doesn't matter what set you consider. Your set is always going to have a least element. In this case, it's 2. In this case, it's 5, right? And what will be an example of a set that doesn't have a least element? Well, okay, this is maybe a bit of a more advanced example, right? Because we haven't talked about what the real numbers are, but if you know what the real numbers are, then you could probably consider the set of real numbers formed by 1 over x, where x is a real number, and this, or let's say these are positive real numbers, right? So now, maybe you are familiar with the idea that as x becomes very big, these numbers become very small, but they will never become 0. So 0 is notably not a part of this set, and this set does not contain a least element, right? Because the least element sort of would be 0, but it's not in there. So any element that you potentially think could be the least element is not actually the least element, because you can always get smaller. So this ordering of real numbers, that's not a well ordering, for example. I hope I am not saying something that is not correct, but I think this should make sense. So for this reason, the ordering of the real numbers is not a well ordering, but it is a total order, because any 2 real numbers can be compared together. Okay, cool. Anyway, back on track. So if you have a set of natural numbers, right, or a subset of the natural numbers, a set containing only natural numbers, then it contains a least element. Now, finally, like that's pretty obvious intuitively, but finally, I would like to maybe try to prove that, right, or kind of prove that, right? So is there some way that we can justify that statement? Okay. Now, there could be some meta logical details of what induction is. Can we do induction, etc.? But let's just try to make an understandable proof of this very intuitive statement and not worry about like all the technical details, because it's very easy to get lost in the technical details, even though like logic and that type of thing can also be very fun. So what's the idea? Well, basically, we can just start listing or going through different natural numbers. So 0, that's a natural number. Then we can ask, right? So let's say we have an arbitrary set S, right? And S is some set that contains natural numbers. So for example, maybe S could be 99 and 4, right? Now, of course, for the general argument, it can be any set, but let's consider this example. So first, we look at 0, right? And then if 0 is in this set, then it must be the smallest element, right? Because 0 is the smallest natural number. So if 0 is in the set, then it is the smallest. So then the smallest number is 0. But if it's not in the set, then we can ask whether 1 is in the set. Now, if 1 is in the set, then we know that 1 is the smallest element because it was not 0, but 1 is in the set, so therefore 1 is the smallest element, right? Because it would have been 0, but 0 wasn't there, but 1 is there, so it's 1. But if 1 is not in the set, right, then we check whether 2 is in the set. And if it is in the set, then the smallest element is 2, obviously, because 0 and 1 were not in the set, but 2 is in the set. So 2 must be the smallest element in the set. But if it's not in the set, then we can keep going to 3, and then we can keep going to 4. And in this case, we have 4 in this set, right? So we find that 4 is in the set. So therefore, the smallest element is 4. And indeed, it is 4, right? So this is an algorithm that in practice, like it can go on forever, and it will always find the smallest element, right? Now the question is, does this algorithm ever terminate? You know, do we actually finally say, yes, this is the smallest element for any set that we could choose? Well, any set containing natural numbers is, let's assume it's not empty, right? The empty set is a bit of a special case. That obviously has no smallest element because it's empty. But if our set is not empty, then our thing will always, so let's say, so for example, S is not empty, and we can prove that by stating that 99 belongs to S, right? So therefore S is not empty. But if there's an element of S, right, we know that this algorithm is going to terminate by the time we reach 99, right? It could terminate before we reach 99, but certainly at the very latest, it's going to terminate. It's going to terminate by the time we reach 99, because 99 is in the set. So therefore, this algorithm says that 99 is the smallest value if we've gotten to that point, right? It's also possible that we've terminated way before 99, such as in this case, we terminate at 4. But in both cases, the algorithm terminates. And this is actually reminding me suspiciously of the axiom of choice, right? So, you know, I could be wrong, but I think, and if you don't know what the axiom of choice is, don't worry about it, basically. But I think this argument for infinite subsets of the natural numbers, I think this argument requires the axioms of choice. I could be wrong, or maybe you can use something else. Maybe I don't know. I'm not sure about this, but anyway. So this algorithm will always terminate for a non-empty subset of the natural numbers, because we can always take some element from that set because it's non-empty, and we know that that is an upper limit for when the algorithm will terminate, right? Okay. Now, on the contrary, Like, let's say we wanted to formulate a similar proof for the largest element, right? Because a subset of the natural numbers does not necessarily contain a largest element. For example, all the even natural numbers, that there's no largest even natural number, right? So if you try to formulate some sort of similar algorithm here, I don't know what it would look like exactly, but presumably it wouldn't terminate, right? So it's not obvious that this algorithm terminates, but it does by this argument. So therefore, every subset of the natural numbers has a smallest element. In this case, it's 4. And we can find it by this quite trivial algorithm, which is bound to always terminate for any subset, no matter if it's finite or infinite. And that is why the set of natural numbers is well ordered. Well ordered. Okay. And I guess that's about it for this video, right? I think I covered everything I wanted to cover. So maybe we could go back to the start real quick. So here we covered the natural numbers, which we initially defined as von Neumann numerals, right, in the previous episode. Of course, we didn't even touch this definition at all. We just didn't worry about it at all. But it's still good to know that, you can define your natural numbers set theoretically. And we went over addition. We did not go over multiplication. I think that's going to be next time. I did that deliberately because I think multiplication is sufficiently kind of scary and weird that I want to cover it separately. We went through all these different order relations. If you had a partial order, that's different. That's many skyscrapers, many trains. But if you have a total order, then that's just one big chain. And the natural numbers are well ordered, meaning every subset has a least element. Actually, I didn't prove that there's infinitely many natural numbers, but maybe you could try to prove that as homework. So try to justify to yourself why there's infinitely many natural numbers. And if you're not familiar with proof techniques, then I remember looking up proof by contradiction. I think that should probably be helpful for you. So you can do a proof by contradiction to show that there's infinitely many natural numbers. So maybe that could be homework for you. Yay. Commutativity, associativity, both properties of addition. And associativity, it's this PlayDough property where you can do something from both sides in whatever order. And commutativity, that's very simple. You just swap them around. And usually it implies this sort of symmetry of the arguments. So the distance between 2 points is a commutative operation. But notably, I would not consider multiplication to be particularly symmetric, even though it's commutative. So multiplication is very weird. So, we're going to get to multiplication in the next episode probably. And then I went on a weird tangent about unary and binary operations too, and the arity of an operation. I hope you found that interesting, and I'll see you in the next one. Goodbye.